Now, previous session we proved that the set of reals, big R, is uncountable. In other words, there's no bijection, there's no correspondence can be found between big R, set of reals, and the set of positive integers, the set of natural numbers, the set of countable numbers. Alright? Now, that piece of information is very useful to us now, because we're going to use that critical piece of information to show that there are languages that are not decidable and not even Turing recognizable. Remember, the set of Turing recognizable languages is larger than the set of languages that's Turing decidable. Now remember, to decide language, the Turing machine, the language is decidable. A bit of revision here again. The language is decidable if there's some Turing machine that decides it. And what does that mean? It means that the Turing machine will accept every string in the language, and it will reject every string that's not in the language. Right? That Turing machine always halts. It never, what's the word, loops. It never loops. Now, a language is Turing recognizable. What does that mean? It means that there's a Turing machine that recognizes the language. And what does that mean? It means that the Turing machine will accept every string in the language. And that's it. There's no further specification. And what that leaves open is that, say, so you might have this Turing machine that recognizes the language, but how does the Turing machine behave when it gets a string that is not a member of the language? What does it do then? Well, it's not specified, so it could either well, it could do any of three things, I suppose. I've not really thought about all. What does it do? I suppose it could accept, reject, or loop, right? But to be a recognizer, that if a string does belong to the language, it will be accepted by the Turing machine. So such a machine, such a Turing machine, is called a recognizer for that language. Right? Well, now using this diagonalization type proof, we now have a tool, a very powerful tool, to show that there are languages. Not only are they not decidable, they're not even Turing recognizable. Okay? That's pretty significant. I mean, if you think about it, what it means. You know, we're getting to the point where there's some tasks that you just cannot solve. That's where we're headed. But we still need, well, we're getting closer. Next session, get quite a bit closer, but the real crunch will come next board, so we'll have to wait a bit, I'm afraid. Okay, so so this diagonalization proof has a very useful application. And the application is to the theory of computation. Surprise, surprise. And it shows that some languages are not decidable, and they're not even Turing recognizable, as I was saying a bit earlier. Okay. Now here's some new stuff. Why is that? Why? Now I'll give it to you in a sort of hand-wavy way, and then we can do it more rigorously in a proper proof, but to give you a feel for why that's the case. In other words, why are there some languages that are not even Turing recognizable? Well, the answer is that you can form a bijection between Turing machines, the set of all Turing machines, obviously an infinite set, and the, well, big N. Right? We'll have to show that, but I'm just giving you the qualitative, well, semi-qualitative argument to start with, so you sort of see the big picture, see where we're going. So you can form a bijection, a correspondence between the set of all Turing machines and the set of the positive integers. Okay. And on the other hand, you cannot form a bijection between the set of all languages and N. Right? In other words, there are more languages. The size of the set of languages, set of all possible languages, is a bigger kind of infinity than the set of positive integers, big N. Okay? Now if you accept that, so that what that means is that given there is a bijection between the set of Turing machines and N, and there is not a bijection between the set of languages, all languages, and N, that means that the set of languages is a bigger kind of infinity than the set of Turing machines. Okay? Let that sink in. We're really starting to get somewhere now. Okay, we'll assume that it's sunk in. There are more languages than Turing machines. Okay? Now, a Turing machine recognizes one language. If it recognizes a different language, well, it's a different Turing machine. Okay? So, one Turing machine, one language. So that means if there are more languages than there are Turing machines, and the mapping, let me think, the mapping between the set of Turing machines and the set of languages, that mapping is 1-to-1, but not onto. Okay? You with me from the previous board on definitions of what 1-to-1 mapping means and what an onto mapping means and what a injective, surjective, bijective, all that stuff. You really need to have this memorized. The notion of mapping is really important for all these proofs. So a Turing machine recognizes one language. So the mapping between a set of Turing machines and a set of languages is 1-to-1. But the size, if you like, of the set of languages is larger than the size of Turing machines, because you cannot form a bijection. There's no correspondence. Therefore, there are languages that cannot be mapped to from a set of Turing machines. There are languages that has no Turing machine that can recognize it. Right? There's, well, I'll give a kind of mini trumpet roll. Ta-da! We'll do a much bigger one next board. That's the essence of the proof. Okay? There's just simply a larger order, a bigger kind of infinity when you describe the size of the set of all languages, all possible languages, than the size of the set of all Turing machines. Okay? So what we need to do now, that's the big picture, the main idea. What we now need to do is to prove that there is a bijection between the number of Turing machines and big N. And the second thing we need to show is that there is no bijection between the set of all languages and N, set of positive integers, set of natural numbers, countable numbers. 3 ways saying the same thing. So we've got down to what? So these languages that have no machine that recognises them, so they're not Turing recognizable. Okay. Right? Now this idea we'll put in the form of corollary. So some languages are not Turing recognizable. In other words, there's no machine. There's just too many languages. There's not enough machines. Right? If we're mapping the machine one-to-one with a language, a Turing machine can recognize one language. Okay, so this mapping is one-to-one, but it's not onto, because there are more languages than there are machines. So there'll be languages for which there's no machine to map it to, right? Or from. Okay. Right. So let's the proof. So. Let's prove that the set of all Turing machines is countable. Okay, and then the second part of the proof, we need to show that the set of all languages is uncountable. Okay, and therefore there have to be languages that don't get mapped to from the set of Turing machines. Right? That mapping cannot be a bijection, cannot be a correspondence. Alright, so let's so it's two parts. So how do we how do we show that the set of all Turing machines is countable? How to do that? Well, we need an intermediate step, and for a given alphabet, that's implicit, I guess. Well, yeah. So here's an alphabet, capital sigma, and it's sigma star. So it's all possible strings that you can form